Okay, welcome everybody to the last day of this meeting. So we have in the first session we have 3 talks today by Annapurni, Ravi, and Prerana. So we'll start with the first talk, Annapurni.
So only the pointer slide is there. Good morning. Thank you, Moshmi and Sudhanshu, for giving me a chance to talk about Magellanic clouds. I can hear you. You can hear me?
A little louder.
Louder. Is it better? No. Yeah. Is it okay now?
Yeah.
I remember the last take, which was a public talk, I ended up actually holding the mic close to my mouth because it had to be louder. So, so thanks for giving me a chance. I recently haven't spoken about the Magellanic clouds as a topic because though I've been working on several years, but mostly I've been talking on other topics which I've been working on: binary stars, boost stragglers, star clusters, etc. So, so this the talks the content of today's talk mainly comes from Sipra's thesis and Dhanush's thesis. Both of them, Dhanush has completed and completed his Viva recently, and Sipra's Viva is still awaited. So these are the main talks, and they're the collaborators. Smita has been working on with us as well. So just give an introduction to Magellanic clouds. I mean, you can see them in the sky in this plot, in this previous slide itself. This is the Milky Way, and these two are the clouds. This is the large cloud, this is the small cloud. This is how you see it in the southern hemisphere. Though it is quite far apart, but this is quite prominent in the sky as a cloud. So small is difficult to, I mean, that's how what I have found. Large is easier to spot in the sky. Small is a bit difficult. So this is generally, so this is the thing you see in the sky, but if you look at the radio, you can actually see a huge, a lot of interaction, a lot of signatures over here. So this is a large cloud and small cloud is somewhere here. So it is a huge plume of things. So optically, if you see, you don't see any kind of any signatures of interaction between them. They appear to be two independent things, but the radio clearly tells that there's been a lot of interactions. And since this is in the south, traditionally, historically, it started getting attention, or rather, science-related understanding came later because you need to set up more observation facilities in the south, including radio. So it took a while to come. So this is like a lot of things happening over here, and this thing is it's going around here. And one more thing I wanted to mention is that when I started my PhD thesis in 90s, it was thought that these are binaries and these are going around the Milky Way more than a few times, etc. But then later on, important thing which we did not understand is the mass of the galaxy as well as the velocity of these clouds, how fast they are moving, etc. Then we got to know that actually they might be going through for the first time, but then still possible that it can be second time, but they're going come into the picture for the first time. So understanding what is influencing what, and what are the how do we see the interaction as, and what are the plumes, how they formed, etc. Some are understood, but some are still difficult to understand and still being probed. So this is an ideal case to study in our own backyard because many such things which happen in the outer part, and we don't have the resolution to do it. But here, as is shown here, this is the whole picture, and then these are the bridge and the small and the large Magellanic cloud. Thanks to Sipra for sharing these slides. So these are the parameters of large cloud. So this is 50 kiloparsec away, off-centered bar is seen. We studied a lot about the bar earlier, but it is not actually a bar in the terms of if you see it in the other galaxies, right? It's not an active bar in terms of gas, but there is still a stellar density out there. And people have tried to find imprint of the bar in terms of kinematics in star or in chemistry, etc. It is there, but gas, it is not there at all. So we really do not know when exactly the bar got disturbed and gas part of the bar got actually dislodged. Right now, the gas doesn't show any typical bar signature. It's metal poor as well. This is the SMC part. SMC, though people call it as this bar, it is actually not a bar, it's just a singular density. And the main problem with this is the actual structure of this galaxy itself is not clearly understood. Initially, we think that it's actually a spheroid or ellipsoid, but the young stars actually tend to show disk kinematics. So transition from ellipsoidal to disk, how exactly it happened and what are the typical things, we still not very clear. I mean, we have been claiming as well from my own group and others, but still it is difficult. But we clearly see the transition to younger population as the disk. It's still further metal poor. So these are the Magellanic, this is the bridge and this is the stream. And these are the leading arms. So there are a lot of gas in front and back, etc. So tidal and various types of interaction are required, but it's still difficult to explain most of this gas in front of the system. Back behind, you can actually explain its tail and gas strip from it, but still, like, you can consider them as jellyfish galaxies or something like that. But still, this is still difficult to explain. So these are the overall things. So the important, what is different in the MCs is that they have poor chemical enrichment, rich in gas, vigorous star formation near a starburst, actually 30 doors. So if you look at star clusters as such, if you look at our galaxy, we have traditionally the large globular clusters and the small open clusters, right? So this direct division is there. In LMC, that division is not there. We have a small number of typical, like the traditional globular clusters are there. Then we have actually massive clusters, of which the counterparts are not there in a galaxy. So we do not know how these, actually the small galaxy was able to produce these massive clusters. Then our studies, as well as the other studies, have found that they do have open clusters like our systems, like towards the lower mass end. But the higher mass end of the open clusters cuts off in our galaxy, but in LMC and SMC, it increases. You do see massive young clusters, which is not there in our galaxy. So that formation, how did it help? How actually it formed, we still do not know. There's some dynamics and all that is there. That's also not clearly understood. But the point is, if you want to study large number density systems in young systems, is actually the place to go for, because there's no other counterpart nearby. And these are stars are resolved. So you can actually see the resolved stellar population, study the resolved stellar population here. 30 Dor is the nearest starburst region. There's no other counterpart nearby. Rich star clusters, gas kinematics, there's no system of bar. No direct evidence of the halo, that's also not clearly understood. The structure of the SMC is still not clear, the nearest interacting pair, so individual stars can be resolved. And since it is at a declination of 70, it's off the galactic plane. You can actually see it without much of an extension. So extension from the galaxy is also less. So this is, so what we have, I'm not going back to the earlier studies. So this is starting from Dhanush's thesis in the last 5-year study. So Gaia, if you look at entire thing, so if you want to study the entire stellar population and understand the interactions or what happened to these clusters, how the populations have changed over time, then you need the large scale data. Small scale data will give you smaller pictures. That's not going to tell you the entire thing. So you need to look at in a larger, so large surveys were very important. So Gaia has given us that, though it is not very deep, but still you can cover the large area. And it also gives us kinematics. So these are the two important things. You can actually locate them and get their kinematics. So this is the full picture, and you can see the younger population extended over here. This is the LMC, this is the SMC. So if you look at, so people have studied the stellar population, the Gaia team themselves have done it. But what I wanted to do was the clusters. How do clusters behave? Because clusters give you, why clusters? Because if you want to study the evolution of the systems as a function of time, you need to look at tracers. And the tracers have to be age dated. So you can look at, Cepheus, they have a particular age. Arlyrae, they have particular age. Redclum, they have particular age. But if you look at clusters, you can actually get the age of individual clusters. So you can actually map how the evolution of this galaxy has happened over time using clusters as a probe. The only problem is you need to make sure that you identify clusters and get their members properly. So that's where the challenge is. But if you can do it, then it's actually a wonderful thing to actually understand not only the formation, but also evolution as a function of time, and not like that kinematics also. So it's a bundle of, I mean, the entire package deal will come. So it's good because there is a cluster catalog from here, and you have the entire set of data. Now, all you have to do is that put this catalog over here and get the data from Gaia and identify the members and make the ages of the clusters and actually get the kinematics. Then you can actually understand entire evolution. So this was the whole aim of Dhanish's thesis. So this is the whole entire cluster distribution from this is about, I think, 4,000 to 5,000 clusters. But there are problems because if you can see, some clusters are merged. If you look at what you will do is you look at spatial distribution of stars and extract this thing, right? But sometimes two clusters are overlapping. Sometimes your clusters totally overlap or partially overlap. So you have to remove certain clusters which are totally overlapping. Partially overlapping clusters were considered, and you have to remove the field star contamination. So there were several steps they developed to actually do this. And so you can actually several types of cleaning, etc. The main thing is to estimate the age and make sure that you estimate the age properly. So I'm not going to the details. You can actually look at his publications. So this is Dhanish's 24 publication. So actually we got 847 new clusters in LMC and 113 new clusters in SMC. So these were in the outskirts and they were important to understand the age dating. So what we got was so what I mentioned was the number of cluster fraction formed as a function of time. Now you have to normalize it because the SMC has less number of clusters and LMC has large number of clusters. If you want to compare them, you have to normalize it. The most importantly, you get a joint peak a little beyond lofty 9. So there is a star formation which has happened in both the galaxies together. Then there has been this kind of wave formation in peaks in SMC. But I should also say that the number is quite less here. But then after this peak, there's a kind of an increase here, and then slowly it reduces. So this is the pattern for the LMC. Now, how they are distributed, you can see the function of time. In LMC, you can see that the older clusters the galaxy was actually quite big when the stars started forming, but then it shrank. And the younger clusters are actually only in the center, and there's nothing outside. So it's basically the galaxy has lost stars, and actually the entire disk has shrunk over a time scale. So that's what the cluster says. And LMC or SMC also, you can see the kind of shrinking, but extension towards the east, which we have already seen in the previous thing. So this is basically the gas moving around, how the gas distribution was there at the function of time. The gas basically came to the inner regions, either because the gas is stripped off or it actually lost the angular momentum and fell inside. Both are possible. So these are the peaks. So if you look at the age-wise distribution, that's what I said. So for less than 1 giga, greater than 1 giga, older clusters, you can see entire disk and large number distribution over here. But if you come less than that to about 500 million years, the entire thing shrinks. The entire this side, the clusters are reducing. It's very likely that the LMC is moving in this direction. The gas is stripped off from the other side. So this gas stripping, and then you can see bar formation. Bar is not present here. The bar is present here. The bar is clearly seen in this age group, 500 to 100 million year. 100 million year younger than that, you don't see the bar at all. You see only the northeast, the 30 door and the star formation. So the gas is still more on the northeastern side. This is how the galaxy is moving. The rest of it is actually doesn't have much of star formation. So this actually tells you how the star formation distributed. Again, with SMC, centrally it is okay, but this kind of things are happening as a function of time, and you can see this extension which is towards the bridge. So moving on to the kinematics. So how do you do? This is the you take with respect to LMC or the LMC I'm showing here. So you have to use this particular north-south axis. Then you have the proper motion plane with respect to north and west, east-west. Then you actually have a position angle because the galaxy is tilted towards you with respect to this angle is the position angle. So you have to actually estimate this I and deproject it. and that is how you find out the in-plane motion of the galaxy. You have to actually correct for it. So this is solving simultaneously, you have to solve for multiple parameters. So what you get it from here is the common center of motion, the center of mass motion of the galaxy, as well as the internal prop motion. That's how you study the internal kinematics. So when you actually put everything together, you see this kind of a pattern, because it's actually moving, everything is moving. It's moving internally as well as moving on the sky. So you have to deconvolve the total motion of it, and then you get the internal motion. So once you take it off this for the LMC, you will get the circular motion. So this is plotted for clusters, and this is for the nearby field. So what we have both data for the cluster and the nearby field. So you can actually get the median prop motion of the cluster and median prop motion of the field. So checking how the clusters behave with respect to the field as well. Because when the star formation happens, the clusters can actually have a different kinematic with respect to the field. Field, what you get will be the overall, the settled down kind of a mean motion. So it does look different because this is slightly disturbed, but this is actually quite low perturbation kind of a thing. So it's not kind of heated up, but this is kind of heated up. So you can clearly see here as well, the cluster is heated up. And you do see a rotation curve with respect to the disk. So here is the 3D perspective of the distribution with respect to, if I can play. So at some point you can actually see this to be like, double. Yeah, this is, it kind of wavy kind of a pattern it comes. And warps, and the inclination changes differently. That is what is shown here. As a function of radius, there's a change in position angle and inclination. Together, you get this kind of a different kind of a warp. And this also is further studied by Smita and her students, this as well. Moving on, we also see interaction. So the point was to see whether there's any change in changing any parameter with a function of time, where you can actually see there's a belief that around 200 million years these two galaxies collided. So can we see any imprint of them? You can see this, that around 100 million years the inclination kinds of changes here. Same thing with position angle. So we think that there may be an interaction happened, and this is how a sudden change has happened, but then later on the galaxy settles down. So the clusters formed around this time is showing a different property of the disk. So it might be that this gas got disturbed there, and the clusters formed from that gas is showing a different perspective. So some kinematic signature is also there. So moving on, yeah, the same thing. So we also see that the clusters do have the overall, let's say the heating up, right? So you can actually see the overall residual prop motion. The residual is more in the clusters. The field is more or less settled. So even though it might have collided, but the overall field is not showing much of a ripple. Because if you two systems you put together, there could be heating and interactions which actually can give you a large residual, which shows that if you have a model, if the particles are not fitting into the model, you get large residues, and that is expected when there is a disturbance perturbation. So, but this is not showing much of a residue here. But here the cluster is actually showing the residue. You can see the residue along the bar as well. So there probably the bar kinematics is also playing a role here, which we model, and we think that the SMC probably the collision went through somewhere around 150 million years and less than 10 kiloparsec. So this could have been the collision. With respect to SMC, the population location itself is different. The red clump actually gives you an ellipsoidal shape, but the young stars give you a very, very different distorted shape. This again tells us that the galaxy has lost gas in the process of moving through the interstellar medium. And we could not model it as it's just a 3D thing. So we modeled it that way. And the morphology of the disks is shown here, assuming it is a disk, but it's a thick disk. It's not a thin disk. And it flattens spheroidal. So there is also a video here of so the green is the red clump and the other two are. So basically this galaxy is kind of turning, and that the large di by dt over a time scale is because of this interaction. So the galaxy has an angular momentum by itself. And that's what you see here as when you see each population, the angle is changing. Such large variation you don't see in LMC. This is because of this interaction with them, which was earlier suggested, but we get it as well. So you can see this change in the colors. Basically, if you see each population, the formation is different. The gas is shifted actually. Yeah, I'm sure. So this is also with respect to that. I'm just skipping that. So coming to small Magellanic cloud, this is the most interesting part of it, that this is the stellar population, and the wing shows the morphologically different as well as kinematically different. You can see the younger population having a larger prop motion, which means that it is actually moving. It's heated up as well as probably moving towards the LMC. But the other one is the stable galaxy. So the gas which got pulled is where the new stars are formed, and they have the kinematics of the disturbance, carry the kinematics of the disturbance. So view from the SMC gives us a help to understand the massive stars. So this is the Galax and UIT studies. This is from Cipra's thesis. So Cipra actually studied a lot of observation footprints, apart from some footprints here as well. It's not marked here. But these entire footprints, which are observed by UVIT in one filter in the far UV. So she has made a catalog, and this is the entire view of the catalog and the main body and the shell, and there's also inner wing here. The summary is the total 93,000 stars. The main body and the inner wing will have 78,600. At the northeast outskirts, we'll have 14,400. So these are the mini stars are more than 8 solar mass, so the massive star. So this actually is an extremely important catalog by itself to study more stars and different types of stars as such. So the kinematics part, if you see, you can see the young one, young two, young three. These are youngest, then little older than that, and older than that. So if you look at the kinematics, you can see that the larger prop motion is seen for the eastern part. Same here, the eastern part is moving more towards the LMC, and this young stars, which is shown here, is same thing as you see here, but you could spatially identify that it is more affected in the eastern part of it and not the entire galaxy. And so there are other results I'm not showing, but the important thing is that one particular part over here, we have 8 filters like far UV4 and near UV4. You can actually create the entire SCD. If you don't have the ultraviolet data points, your SCD will stop here. Okay, so if you actually see, if you see the UV part, this is covering here. So here, if you cover the UV part, here is an example where without the UV part, you will not actually be detecting the hot companion. You'll be seeing only the cooler companion. Here, with the help of the UV, we are able to identify that this kind of a system has a UV companion. And the confidence comes because we have 8 data points. If I had only 1 or 2 data points, it's still questionable. But 8 data points, it's very hard to turn it down. So the idea was to make sure that how do we get such systems, and are such systems there, and can we confidently estimate their parameters? So we've taken only a very conservative sample here. And so these are the things. The blue ones. So you don't expect any star bluer than this main sequence. All of your stars are supposed to be here. But in the binary companion, which you are showing here, this blue things, if you actually get their parameters and put them, they are actually here. So these are candidates for strip stars. In binary systems, these cannot be produced by single star revolution. Only there and here. All can evolve on this path. And when they become white dwarf, they are here. So this is actually a large gap area. So these you see are the strip star masses shown here. So we see that large number of strip stars are there, and their masses can vary as well. So without UV, you can't actually get to the strip stars, particularly because the optical doesn't cover that particular area. So she has got a lot of them and characterized them as well. I stop here on this. So there are interesting, many of them here. Each one can be actually probed and found out what their period is, other properties are, X-ray properties, and what they formation mechanism, etc., and all that. So it's a gold mine but there's a lot of studies to be done. Yeah, stop here. Thank you.
question. So you can ask later.
So that strip gas which is in the northern side, we are understanding how that is formed. And to show the radio picture of the Magellanic stream and then the gas on that.
Yeah, the front side, the front side. They do think that there are several mechanisms, but the tidal thing itself, there are models which tells you that tidal things can strip thing while they're orbiting, can throw gas in the front, but not very clear. But there's some other studies saying that it could be mergers or some things happen apart from these two galaxies. So I'm not sure, Smita, you can add if there are any newer.
Also, it's a strip gas belonging to the mystery.
No. Yeah, it's not very intuitive, but yeah.
I wanted to know this, that Milky Way has a precision of 2 kilometers per second kiloparsec. Like in LMC, you also showed that there was a warp kind of feature. Do we have some such measurement or precision rate for this warp?
No, we have not looked at the warps at the outer side, but Smita and Sarun had a paper on looking at the warp on the outer side. We did find a warp when the data was small, and we did find a warp in the initial part. I think it is part of Smita's thesis, but now we have data very large and we can actually look at it. That's what they did. We haven't looked at the kinematics of the warp. Do you know the kinematics of the warp? Yeah, maybe a good thing to look at. It's not easy to do that, right? You need to. The problem is the position angle and the inclination is changing. In the Milky Way, you have a different way of looking at it. Here, you need to define what the galaxy is, and then only you define the warp. While defining the galaxy itself, you cannot fix the inclination and position angle because it's changing as a function of radius. It's also changing as a function of population. So it's not an easy thing to do. You can't isolate.
Okay, thanks for again. In the last video. We move on to the next speaker, Ravi Joshi.
So good morning, everyone. I would like to thank Moshmi and Sudhanshu for giving me the opportunity to present the work. Actually, I thought I'll take this as a challenge to finish my feedback work in a month time, which I could not do. So now I've changed the topic. So I'm going to talk about and this has been also iterated many times. Dharam has nicely motivated why we should study the dual and binary AGNs. And so I would like to present our recent work to understand can X-shaped radio galaxies be the potential candidate to find the dual or binary AGNs? Yeah. So I think now we very well know that finding the binary AGNs and dual AGNs is very important to understand the overall growth of galaxies. However, the primary challenge to do that is at the first place to find those candidates, right? Especially the binary black hole, because detecting them is very difficult because we don't have that kind of spatial resolution. That is not only primary condition, but there are other effects. For instance, there is an AGN duty cycle associated with detecting the AGNs, right? You may detect one AGN as an active phase, but the other won't. So, so what one has to do is that one has to rely for the indirect indicators. One such indicator is the periodic variability in AGN light curves. Essentially, if you monitor the AGNs for a very long time, say 10, 20 years, people do have seen the periodicity in the AGN light curves, roughly 4.1% of quasars, and OJ287 is a good example of it. You can also look for the periodic variability in or you can look for the AGNs with a double peak broad emission lines and look for the periodic variations, how the lines are changing. It's a very small number, 0.05% in the total population. Or you can also look for the narrow emission, double peak narrow emission line in the spectra. You can also look for example, the same thing from the radio side. You can look for the jet precessing around the galaxy, or you can look for different kind of radio morphology. For example, as Dharam has highlighted, X-shaped radio galaxies or Z or S-shaped radio galaxies, or you directly detect it through the gravitational wave, right? So X-shaped radio, why X-shaped radio galaxies? It's very clear from the image itself. This is an image taken from UGMRT. If you compare these X-shaped radio galaxies with the normal radio galaxies, what you see is that you do see a one jet having the hotspots, which is quite resembling with the classical FR2 kind of radio systems. You also do see another set of jet which is diffuse in structure, resembling the FR1 kind of morphology. Meaning is that one can think of is that what if this system has two black holes and sending their jets in two different directions. One is this, another one is this. So that makes it interesting sources to follow up for the finding the binary black holes. This kind of objects have been discovered very early on in 1992 by Lehe and Perma. They have discovered 11 such objects. Okay, and so people have studied like what could result to the formation of this kind of structure. And there are several models proposed. One of them is the backflow divergent model, where you can consider that the plasma moving in one direction. When it backflows, it will simply go to the pressure direction, low pressure direction, and then they will naturally forms the X kind of structure. There are other scenarios also proposed. For instance, that's called jet reorientation. If merger happens, the primary jet can reorient. It will stop, and the new jets may start in the different direction, making an X-shaped structure. The first jet, if you see, that is now in diffuse nature because it's aged now. So these are two. So given that we have not.
In this case, they have to be the center has to be same, right?
Center has to be same.
It's not center is not the same.
Here also center is same.
You have to have the center. The things are like offset from the center, right?
Oh, you mean in this case?
Yeah.
Oh, not necessarily, because the jet can bend actually, depending on the density. So you can have like slightly offset. They come in different shapes essentially. That sometimes the secondary jets start from the center. Sometimes the plasma comes and then it right deviates from the galaxy center. So it's hard to distinguish given the resolution of the data. Yeah. So now this makes basically the objective twofold. One is we have to understand like which is the mechanism working to form this X-shaped structure. The second thing is that are they really potential candidates for the binary black holes? Well, until recently, till 2019, there were very limited set of X-shaped radio galaxies were known, only 100 in number, and that was discovered in 2007 by Chung. And then, like when I was doing my second postdoc, while discussing with one of the other postdoc fellow, we got interested in searching the binary black holes, and we thought that okay, X-shaped radio galaxies are a good candidate, but we realized the sample is very limited, only 100 in number. You can see like all the structures, you do see a FR2 kind of morphology and a very diffuse structure, but the sample is of course limited. So the idea was to first increase the sample at first place. Yeah, this is mostly by eye. Yeah.
Any particular wavelength in radio that it's used to classify that it's X-shaped?
Mostly it is like given the first is the readily available survey. To begin with, it was first, but the later people are using LOFAR and even we use the TGSS. Yeah. So the idea was to increase the sample, and what we did is that we have used two catalogs. One is the 1.4 gigahertz first, and we also use the 150 megahertz TGSS survey. Given that the frequency is low, this is sensitive to detect the diffuse structure. First, if you look at, it's a very wide sky survey with almost a million of point sources detected, and we checked roughly about 6,000 sources and found some very nice example of the X-shaped structure. So if you look at these black contours, these are basically the 1.4 gigahertz first maps. You can see that for example, this case, it's hard to say that whether it's X-shaped or not, but you overlay the PGSS maps at 150 megahertz, you can nicely see that, okay, it has a diffuse structure in a perpendicular direction with respect to the parent jet. Okay. So now given that, so with this, we have almost classified roughly about 290 XRGs. Among them, 106 we assigned as a very strong X-shaped radiogalaxy candidate. Now, given that this is almost like a threefold of the sample, which was earlier known, we thought of now understanding what is the region for this morphology. And to begin with, we started with studying the optical host properties of these systems. You can do a simple experiment where you just take the optical host and try to look for any correlation between the major axis of the optical host versus the radio jets, what we see in these galaxies. And that's what we did here. This is the basically major axis of the galaxy. And you just try to find out the axis for the wings and the active jet. If you just compare it, here is the top panel. It just compare basically the position angle difference between the active jet and the major axis of the host galaxy. And you see, preferentially most of the time, the major jet aligns with respect to the major axis of the galaxy, whereas the wings tells the different story. Okay, and this you can reconcile simply with the backflow diversion, where the plasma will flow back and simply move in these directions. So this supports the backflow scenario. You can look for other properties. For instance, we try to compare these X-shaped radio galaxies with other bright radio sources, for example, FR2 kind of systems. If you compare the black hole mass, which is being done here, so we find that the red ones are the X-shaped radio galaxies, blue ones are the FR2. And we found that the black hole mass of these X-shaped galaxies is a little bit smaller than the classical FR2 sources. You can also ask, what happened to the environment? What's the role played by the environment? If you look at, for example, the FR2 structures or XRG structure, which are having a large jets going up to scale of 100 kiloparsec or beyond, and if you calculate the density or the richness of the environment, it's found that the XRGs and FR2 systematically sits at the poor environment with a richness of 10 to around 10, whereas the FR1 kind of sources, which have a diffuse jet structure, they sit in the rich environment. So that's interesting. But then how about them hosting the binary black holes or the dual AGNs, right? So one can test in a very simple way is that one can look for one can do the spectral index mapping of these sources. Given that if the wings are old, then you expect the spectral index to be steeper. And if this jet is active, where the fresh electrons have been impinged from the center, you expect it to be having a flatter spectral index, right? So one can do that, and it's been tried for a good number of sources by many people, like Dharam also highlighted it yesterday. So this is one of the very nice example, 3C223.1. You see very nice X-shaped structure here. This is the active jet. This is the wing or the passive jet. With the multi-frequency data ranging from 1.4 gigahertz, 1.4 megahertz till 8.3 gigahertz. If you do the spectral index mapping, you clearly see that if you look at the spectral index along the wing and compare it with the active jet, the wings are actually flatter, which doesn't support the backflow model, right? And it may also gives up. It is also likely that probably, the hope remains that they may be a good candidate for searching the binary black holes. So the question is that does this flatter spectral index is a common phenomenon in X-shaped radio galaxies? So we try to understand it first. And given that a good number of X-shaped radio galaxies have been discovered in our data set, we try to follow it with the UGMRT. Here you see some of the nice X-shaped radio galaxies image followed with the UGMRT at 1.4 gigahertz. We have observed roughly about 25 sources, but unfortunately we could not get any data in the higher frequency. So this work is we are still trying to get the data at higher frequency. But then, of course, you can look for the archival data sets. So for instance, what we did is that we have looked for the available X-shaped radio galaxies recently, which is roughly almost 700 in number. Now you can see that the number is growing depending on the surveys are basically coming up. So we found roughly about 40 sources, and in the different frequency ranging from 1.4 gigahertz till 144 megahertz. We try to make the spectral index map for these X-shaped sources. What you see here is that these are the X-shaped structures, and we just draw a ridge line starting from the hotspot and going to the wing on either side. And if in the last column, what you see is basically the spectral index map. So what we found is that we do see basically for most of the X-shaped galaxies, these wings are steeper. I mean, they are the aged ones. They support the backflow scenario. But for
Sorry.
yeah,
The spectral index is computed by using those two frequencies.
frequencies, yeah,
So if there is any variation in between, you don't know.
and we cannot catch. Yeah, it's a broader one. So, but what we see is that for most of them, the spectral index is steeper as expected for the backflow scenario. But for a couple of sources, roughly 10 sources, we do see that the wings are actually flatter than the active jet. It's been So this may likely happen because of the in situ particle acceleration within the jet itself. So this tells us that the flattening of the wings in X-shaped galaxies is being detected, but it's not a very common phenomenon. Well, recently, like with one of the VSP student here, I tried to look for like how can we basically enhance or search for the binary black hole in X-shaped galaxies. As I mentioned in the very beginning, that one has to look for the indirect indicators. One was the double peak narrow emission line, and if you club the double peak narrow emission line with an additional indicator, that the X-shaped galaxies, it is basically enhancing the probability of detecting the binary black hole in these systems. That's been tried recently. So what you see here in the left panel, you see very nice like double peak multiple narrow emission lines coming from these X-shaped galaxies. The radio images are here. So we started with, now using the number has grown to almost 800 now. So with this, we searched them in the Daisy or Sloan spectra and found roughly about 300 sources where we do see a very strong O3 emission line. You just like model the emission line and try to see like for how many of them you see double peak. If you do that, we found roughly about 55 sources having the strong double peak emission line. 4 of them have been followed with the VLBA. And we also try to look for like if anything is available in the archive. So we found 4 additional ones. So we have like roughly 8 VLBA observations, mapping almost on the parsec scales. Well, since you have all the emission line fitted, you can do one simple analysis. You can put them in the BPD diagram. If you put them in the BPD diagram, you clearly see that almost all the sources or both the double peak nature basically sitting in the AGN locus. So for almost all of the galaxies, albeit you have the upper limit for few, but still they're sitting in the AGN locus. So this is promising. What one can simply do is that one can compare what happens if you compare this X-shaped galaxy with a normal galaxy. So let's do it. For example, if you look at the normal galaxies, you can ask like what fraction of them will have the double peak. So roughly 1% of the galaxies in general have the double peak. Whereas if you look at the XRG's systems, roughly 30% of the XRGs have double peak emission lines. You can ask like what fraction of these double peak emission line in normal galaxy with respect to the XRGs have, say, AGN characteristics in BPT. For the normal one, it's 30%. Whereas for XRGs, we found it's almost 95%. Then like one can also compare the two in terms of the control in a sort of controlled way. For example, you can match them in the stellar mass, color, and the redshifts. This fraction is roughly, again, 25%, whereas the XRGs retain to 95%. What it tells is that in the general double peak galaxy population, if you ask for like what fraction of them are hosting AGN, it is just like 0.3%. Whereas for the XRGs, it's almost like 30%. So the question is like, what is the possible link between these X-shaped galaxies versus them hosting the dual AGN? So given that these sources are radio bright, you can simply ask for like what happened when you compare the sources both detected in the radio. So that's what's being done here. The x-axis shows the radioluminosity, and the y-axis is the fraction of dual AGN in these systems. The gray ones are basically all the galaxies where we don't see the radio emission, and the fraction of these systems hosting AGN is roughly 25%. Whereas if you look at as a function of the radio brightness, when they become radio bright, the fraction of the systems hosting AGNs is actually increasing. It's 60% for the normal galaxy, and for the XRGs is almost hitting to 100%. Well, that is promising. Then one can also compare the other properties. For example, you can compare the black hole mass versus the radioluminosity. For the XRGs with double peak or not having double peak. When you do that, actually the XRGs with double peak and single peak, they are no different from each other in terms of the radioluminosity and the black hole mass. That is puzzling, is that then why we don't see the double peak emission line in all the XRGs. So of course, then one has to zoom in the parsec scale. As I said, like we have followed a couple of sources with the VLBI. And here what you see is that few examples. This is the X-shaped radio structure seen in the kiloparsec scale. The inside what you see is basically the VLBI data. The 1.4 gigahertz comes from our observations, where the other come from the literature. So almost like you can see, like in most of the, almost like in none of the case we resolve the core. So it's basically hard to resolve these systems at parsec scale. That's what we found. The other good thing about them is basically if you look at the spectral index in different frequencies, we found that the spectral index is flatter. So if you have better resolution, they may be the better candidate to follow for the to search the binary AGNs. If you look at the optical host instead, almost large fraction of the systems have a companion sitting next to it. In terms of SpecZ selected companion, we have 30% sources where you see another companion. Whereas if you go for the PhotoZ, almost 70 to 80% of the sources have a nearby companion. Meaning is that they are hinting, yeah. Meaning is that they hint that these systems are driven by the mergers. Well, the UGMRT data. So what if like we started with the conjecture that what if the two systems have two binary black holes, two black holes sending their own jets. We have not found any such candidate yet where you see two jets driven by the two black holes in two different directions, making X-shaped structure. But it is likely possible because this is one of the observations we did with the UGMRT. What you see is a galaxy, is a dumbbell galaxy. You see two nuclei, and both of them sending their own jets in two different directions. That is interesting. If one happened to send it in a perpendicular direction, that would lead to the X-shaped structure. We started it with basically, I mean, this direction in the this direction has been thought to be the active jet in the low resolution first data, and this was thought to be the wing, but it turned out to be the two jets. So we are following it with basically a VLA for polarization map. Unfortunately, with the 90 kilosecond Chandra data, we could not detect anything at this location. We were thinking to probe the cavities in these systems, but probably it needs longer time to do that. Yeah. We try modeling these systems further, just to know like what are the characteristics of these jets. So Shantanu has modeled it. It's a hydrodynamic modeling and tells that these systems are having moving at a subrelativistic speed of roughly 0.1 c, and jet precision can simply lead to this kind of morphologies in XRGs or this kind of systems. Well, how about them hosting the dual AGN? This is VLB observations done at 5 gigahertz. And what we showed is that what you see here is a very nice X-shaped structure. The A and B, both the sources were having the same redshift. And when we observed in the VLBI, we found that in both the cases we found the core at 5 gigahertz. At the same time, there is a bridge connecting the two, which we thought is that this X-shaped structure might be led by the merger of these systems. But I'll just summarize here. What we learned is that the X-shaped radiomorphology is more sort of a complex because it comes from different phenomena. It can be a simply backflow, it can be a merger, jet reorientation, or they may host the binary AGNs also, but that of course needs more investigations. So I'll stop it here with the conclusion.
So PT has done VLBI at different epochs after 5 years now.
Right.
So in your case, will that help if you do observation at different epochs?
Yeah, of course it will help, but the problem is that finding time in VLBI is not very easy. Yeah, our idea was to at least get the time for two frequencies. Given that we could resolve only one source, and that too like very mildly. So this one. So a follow-up is needed, but like yeah, it's very challenging to get time. I tried a lot, but it's not okay. Yeah. At least it'll help to disentangle if they are basically jets or the two nuclei.
So many of them are associated with mergers. Right?
Yeah.
So have you looked at UV unique profile of the galaxy? Because if it is merged, there will be a lot of star formation. Right?
Oh, these are mostly high Z stuff.
Oh.
Yeah. Redshift will be, if you look at the median redshift, it will be 0.3, 0.2 to 0.3. And then you can see the size, they are very compact also.
Okay, so they will be redshifted to vertical.
Yeah.
Yeah, I wanted to know whether the initial 100 samples, are they also identified in plant data, for example?
The initial 100 is not ours. Initial 100 done by Chong in 2007. That I'm not seeing if it's in plant data. One has to check.
I guess the angular scales of this would be like what?
Oh, it's that. It's more than 10 arcsec.
10 arcsec.
They have been chosen that way.
But I guess when we go to very small scale CMB, for example, Simon's Observatory is going to go to smaller scales. There, these may become important as point sources, terminals.
Yeah.
So I was wondering whether there is some identification, cross-correlation.
Mostly, for example, if you look at NVSS and other things, they would appear as point source only because.
NVSS, that is very low frequency, so it may not matter much. That's megahertz frequency. That's what
1.4.
Oh, it's, yeah.
1.4. Yeah,
Yeah.
1.4 will be.
Yeah, that's what I'm
in
saying.
that range. Okay, yeah, it'd be great if you find more. Okay, let's thank Ravi again and move on to the. Very nice.
Am I audible? Yeah. Hello, everyone. So first, I'd like to thank the organizer for giving me this opportunity to talk about this work. So this work is basically on the properties and spectral properties of the dual nuclei system found from the GOTHIC survey. So, as we know that galaxy mergers are very interesting in terms of, how they affect the star formation, kinematics, stability, gas involved morphology, and the overall evolution of the galaxies. Many of these topics has already been discussed in the last 2 days. And now when we talk about the galaxy mergers, then it is often found that in a merging system, there are two nucleus, bright nucleus inside these systems. Now these dual nucleus are important to study because from here we can study the co-evolution of the merging galaxy along with this supermassive black hole. Not only that, the different scaling relations that we know holds for the normal galaxies, which are not in merging state, so how they can be affected by the merging of the galaxies and as well the supermassive black holes within them, and also how the star formation, the chemical abundances, the accretion change in a gravitational potential. So along with these questions in the mind, I will go to the next part, which is what sample did we choose for these studies. This is basically has chosen from the GOTHIC survey. I will not go very details, but this is this survey, in this GOTHIC survey, there were randomly chosen 1 million sources from SDSS, and by this algorithm that graph boosted hill climbing, iterated hill climbing algorithm. So there they identified, the 681 multi-nuclei system. I hope you were there in Nehal's talk yesterday. So thank to him that he just described the ground for this sample. And these many sources, which is a total, if I count them individually, are around 1400 sources, which has double, triple, and quadruple system inside them. But mostly the system is, I mean, those sources are, I mean, mainly contains the dual nuclei system. And all these sources, as you can see, are nearby. And I mean, the peak of the median or the distribution is of the redshift is 0.07. And I mean, bright. And also they are comprised of star-forming composite and AGNs. And before going to the study of the spectroscopic analysis and all that, we checked that if in the literature, if it has been already done or not. As you can see that these are SDSS sources. In SDSS, we can already see the fitted spectra and all that. So, I mean, then we checked for the literature and find out that, I mean, what are the overlaps with the literature? We find out that from the SDSS value added catalog, there are these 4 groups which have been doing the spectral analysis of the galaxies. And among them, these above 4 groups have very little overlap with the sample, only around 10 sources within the 3 arcsecond of our sample. But for Firefly, we had the full sample overlap, but the nice, I mean, the advantageous position for us that Firefly does not give us the kinematics, stellar kinematics, but it gives us some, I mean, the star formation rate and other properties, but these are not as updated with the technical or with the methodological advances that we are applying. And I will talk about that in a moment. Okay, so for doing the spectral analysis, what we use is the PPXF, the penalized pixel fixing code by Michael Capillari. So the basic idea of fitting the spectra with PPXF is that we have the spectra, and this spectra is I mean, made of different population of the stars inside the galaxies. And this population of stars have their own properties. So we have our known spectral templates for these different populations. We take the combination of them, convolve them with the line of sight velocities with the galaxies, and find out that how many different kinds of populations are there inside that spectra, I mean, for which the spectra is good fitted. So that's why that is the whole idea. But for going into the details, what we did is that we first started with these all sources and put a cutoff of SNR for, I mean, good fitting. And then we did the fitting in 2 ways. First, we concentrated on the stellar kinematics, for which we marked the emission lines and then run the PPXF. And from there, we found the stellar velocity dispersion, that is the stellar kinematics. And after that, there is a problem. I mean, if you go give any spectra to PPXF, it will in any way give you a fit, but that fit may not be a good fit. And the chi-square or any other properties that we cannot quantify it, that if the fit is good or bad. So what we do, we went for the manual intervention and look for each sources one by one, and which give us the, and assign it with the quality flag. So we took like, if the fit is very good, we put it as a quality flag 0, and nearly good 1. And we took our final sample to be only with the good fit and nearly good fit. And these are the some, I mean, fittings for quality flag 0 and quality flag 1. And these comprised of 915 sources out of these sources, and which contains again around 350 dual system and some triplet, but no quadruple system. So this is the finalized sample for our study. Now, along with that, as I have mentioned, that we first marked the gas emission lines, but for the gas kinematics, we have included these gas emission lines and then run PPXF. And from here, what we got is the light-weighted contribution from the different stellar population synthesis modeling. And these different weightages give us the stellar mass, metallicity, age, mass to line ratio, line flux, etc. So these are the basics. So as you can see, these are some of the fitted spectra in which the gas emission lines indeed included. Okay, so as right now we have these things, so now we went to the consistency check that how our result is in comparison to the previous values that we had. So for that, we first compared the stellar velocity dispersion from the SDSS with our dispersion. And as you can see that they are broadly, consistent with each other, except for some cases where SDSS just gives us 0. And some cases where SDSS stellar velocity dispersion is so quite low or very high, it mentions that they are not reliable. But in our cases, we find that, okay, we are getting, acceptable values for them. So it again also tells us the importance of doing this again with the better modified methodological advances available right now. So, and beside that, we also checked for the stellar masses that how available, because the Firefly group gives us the stellar masses. We compared it, but there we found that there is an offset between the mass that we found and the mass that Firefly group found. But this is not new. This group, Manga Firefly group, they also found out offset between these two masses, Manga group and the Firefly group. But if we consider that the average of the or the median of the Manga Firefly and what we are getting, they are more or less consistent. So which gives us confidence that, okay, the results that we are getting is reliable. And thus with these results, we go on. So first, what we did is categorized or classified them with the emission line-based classification, as you know, with the BPT diagram. So as I mentioned earlier, that from BPXF fitting, we got the line fluxes. So for the line fluxes, with the line fluxes, we find out the differences of the, finalized sources. So now I would like to mention that, for the finalized sources, we only could classify around 45% of the sources because of the, non-detection of the all these 4 lines. But 4 lines. But from if we use the SDSS line fluxes, then the detection rate is little higher. But again, from SDSS, they uses lower SNR spectra, and if even the emission feature is weaker, they also take it into consideration. So I should say that SDSS-based classification is more inclusive but less reliable, but our is more conservative, but mostly, very reliable, the classification. Okay, so along with the classified sources, this is the distribution of the sources. As you can see, these are the stellar velocity dispersion in star. So the star-forming galaxies are at the, as usual it should be, at the lower end of the stellar velocity dispersion. Then comes the composite, and then comes the AGN, the liner, and the Seyfert. And this is true for the stellar mass only. And along with that, we find out the black hole mass using this Carmendian-Hose formula. And Carmendian-Hose. So here I need to mention that this formula of finding black hole mass from the stellar dispersion holds for the elliptical galaxies and galaxies with the classical bulges. But for our systems, it comprises of star-forming ones also. But the nice point is that the spectra that we are taking at the center, and the SDSS spectra has only 3 arcseconds in the radius. And if we consider the redshift of our median redshift, which is 0.07, then the physical length at 3 arcseconds comes around 3 to 4 kpc. So within the 3 to 4 kpc, if it is either a star-forming galaxy or an AGN, or if it has an classical bulge or pseudo-bulge, but within this region, we can consider the system is virialized, and this formula can be applicable. So, assuming this is true, we find out the black hole masses of the galaxies, and here also we can see that it is showing the same trend, that the star-forming one have the lowest black hole masses, then the composite and the AGN. Similarly, we show it for the galaxy ages and the metallicity with and a similar trend is found. Okay, so equipped with that, now we next check the scaling relation, which is the black hole mass and the stellar mass relation. So as you can see, that in general, they are following the trend, like with the increasing stellar mass, the black hole mass is increasing. But in this line, this yellow line is for the this magenta line or the violet line is for all the sources. Then we compared it with the existing literature, this raise and voluntary line, where the AGNs have been used around for 47 lakhs AGNs to find out this equation. But their system is not explicitly consist of the dual system. They can have dual, but they are also have single system. And we can see that if we consider the only AGNs, then this is the line we are getting. The point is there is an offset or the change of the slope between the dual and the system which is not being categorized in this case. So one important thing that we can infer from that the supermassive black hole growth is higher in dual system in comparison to the single system. Apart from, it's not just due to the coalescence, but it is happening in general for the dual system. The growth is higher, slope the higher. Again, also, we compared this slope for the AGN and liner, and it is coming that for the AGN liner, the supermassive growth rate is higher, but in comparison to the AGN Seaford. So this is one of the interesting things that we found here. Besides that, we also found 6 outliers in this plot, which has black hole mass as massive as the stellar mass, which is very interesting. And we later on will like to take a close look on that how these sources are surviving. Okay, so again, coming to the next part is we checked the stellar velocity dispersion with the stellar mass and compared it with the existing literature. Here we found that the existing literature, M star varies, sigma star varies with M star, roughly 0.3, which is a signature of saying that the system is in virial equilibrium. In our cases also, we find that this relationship holds, quite consistent with the existing literature. And what we can say about that instead, in fact, systems which are going inside the merger, instead of going on the ongoing merger, the system somehow, sustained the virial equilibrium inside the nucleus region. And another part is that we checked for the AGN liner and Seaford, and it is showing that AGN liner are more close to the virialized equilibrium than the AGN Seaford. These are the second most interesting findings in our study. Okay, so now how much time do I have? Okay, so I'll go really quick about that. So another is the metallicity. For the metallicity as well, we found that there is some offset, like for galaxies with lower mass, the metallicity is lower in comparison to the single system, and for the higher mass, it is the vice versa case. And also for the age of the age with the M star, we can see that famous downsizing relation. Like these galaxies also, if the mass is higher, then they tend to have faster star formation, and they evolve faster. So this scenario we have taken. And the next part, we have also checked, like for now we are comparing the dual system with the single system. And at this part, what we are doing, we took the dual systems only and check that how the two systems are co-evolved with each other. So for that, what we have first, we separated it into different categories and pairs, what we have, and we found that this system can have all possible combination exist, and also they are going into major and minor mergers. And although the minor mergers are, increased in the number, and we checked that how the black hole masses for each other varies with each other. And we found that, well, so with the black hole mass of the companion 1 is increasing with the companion 2. But okay, here we should mention that how we are defining the companion. The companion with the greater stellar mass is named as companion 1, and companion 2 is with the smaller stellar mass. But here we can see that this line is where these two masses are same. There are some sources where companion 1 has the greater solar mass than the companion 2, but the black hole mass shows the reverse relation. I mean, the black hole of the companion 1 is smaller than the companion 2. So the sources above this line. And we took a close look on that relation, but to check that if there is anything else going on here or not. But within the uncertainty, it is hard to say that if it is showing any interesting result or significance or not. But yeah, there are some inverted relation with that. Again, with the other properties like sigma star, I mean the stellar velocity dispersion, age, and the metallicity, we see that it is more or less with the companion 1, the companion 2's stellar mass, age, and metallicity are increasing. So with that, I will conclude. So the main findings that we got is that, as I mentioned, that the dual systems have the growth of the supermassive black hole in the dual system is larger than in comparison to the single nucleus galaxies. And also the AGN liner showing more growth in the supermassive black hole than Seyfert. And also the stellar velocity, I mean, the virial equilibrium is sustained inside the dual nucleus system instead of ongoing star formation, ongoing merging. And also the mass metallicity relation shows some offset. And for the co-evolution of the dual nuclei, we see that there are some populations where the ratio of the M star is greater than 1, but the black hole masses ratio are, less than 1. So yeah, with that, I will conclude. Thank you. Any question? Any question?
Dr. Ravi, interesting work also. I was just wondering, so in overall of your sample, what is the minimum separation between the two nuclei? Because when we're taking the spectra, whether there is any contamination between the two objects or not.
Oh, okay, so the separation, I had a plot, I can show you later. So the separation is starting from like 4 to 5 kpc. I mean, it is outside of the SDSS fiber. So no contamination is included. So for 5 kpc to it goes like 100 kpc also sometimes.
Very interesting work. So I was interested to know, can you identify the post-merger sources in your case and whether there are bars in those systems? Because those also play.
Yes. So right now, to identify the post-merger sources, the way we have to look at the individual images that we can say. Other than that, also we can, we have already done with Nehal the Galfit for all these sources, but that has not been finalized to check. And with the Galfit results, we can see that what is their, status of the bar, right? If it has, so if the profile says that it has a bulge or something like that, that we can say from the Galfit. But for the bar, we have to do some Fourier analysis, I think, to check. It's the thing. But yeah, it can be done.
Is there any more questions? Okay, so let's thank all the speakers for the moment. Mostly, would you like to give 10 extra minutes for the next session?
Yeah.
Because we overshot the time.
Oh, okay, sure.
Okay, so I think people can meet at 11:40. He was supposed to be around. Yeah, 11:40.
Okay, 11:45 also.
I know, that's why I mean that's very hard.
M star and sigma star, and sigma star is proportional to M star to the power to the 0.3 motorwatt. 0.3 to realize মানে stable হ্যাঁ মানে stable মানে realize মানে ওই dynamic 2K plus B that condition is satisfied in systemic stabilization no more like dynamical changes will be there সেটা বলা মুশকিল মানে হ্যাঁ মানে ওটার কাইনেমেটিক্স হ্যাঁ আন্ডার বাইরে থেকে কিছু হচ্ছে কোনো এবং তুমি সেম কন্ডিশন সেম ক্রাইটেরিয়া ইউজ করেছো যখন তুমি ব্ল্যাক হোলের মাস বের করছিলে আমি ইউজ করিনি আমি জাস্ট অ্যাজিউম করেছি যে ওটা ফিগার আছে ওই পিকচার রিজন ইটস আ ভেরি সেন্ট্রাল রিজিয়ন ভেরি সেন্ট্রাল রিজিয়ন মানে ওই পার্টমেন্টের পোয়েট্রি রিলেশন যেটা এম স্টার আর সিগমা স্টার আর কি কানেক্ট করে সো ইটস অলরেডি তো সেটা আর কি ওরা পেপারে বলেইছিল যে ইট ইজ ট্রু ফর ক্লাস I've been working, but I was not কারণেই হয়তো match হচ্ছে
It's in PDF. That's right.
More talks. I
This
think
is
next
your-
session, 3 or 6 talks.
What is it on how you estimate the errors? Because it's quite complex, right?
Yes, because we did the bootstrapping. I didn't go into the details.
Okay.
I mean, so first we done the PPXF, we got some results.
It's done.
Then we part up the spectrum.
I understand that, but the spectra does
So
have
because
some
of
errors.
Yes,
Yes,
with the
the
errors.
international wavelength, no.
Yes.
It's
So
also
it's
done.
not,
I mean, suppose we have this
All of them are down.
and it has error at each pixel.
PDF, okay.
So take it and put a random point over here. I mean, for each of these within the
the
error.
Gaussian, is it?
The error is Gaussian, and inside the Gaussian, we take a random point at each pixel and create another spectrum. And this spectra is again fit to the PPXF. And we did it like for 100 times.
This is not the actual error folded in.
I mean, for which this is called the bootstrapping. So I mentioned in this, I mean, I had it in the
Yeah,
slide.
but that's not actually.
Actually error, but it's a bootstrapped error. I mean, we use it randomly. I mean, when there is, not straightforward error calculation. I mean, PPXF had with other packages that if you want to compute the errors, you have to bootstrap. So I sandwich that bootstrap code in the PPXF and then find out these errors.
But you have to put limits where you can use and you cannot use.
Yes, that's why these errors were instead of 2 sigma, 3 sigma, we put it in 2 sigma. So the points will be chosen from the 2 sigma.
How many times you do this?
We first did it for 50 times with some of these results, but later on for the paper we did it for 200 times. I mean, we can go more, I mean, the computational time it takes.
Yeah, it has to sample the profile.
Yes. I mean, with 50 also the results are similar. Because
More couple of questions. Are you going to?
Yeah.
Yeah.
Yeah, I've checked.
Right.
You can wear it. I'll just wear, yeah, it doesn't matter. You don't have to see. You can just wear it. And people actually wearing like this. From my 10K. Yeah, but can be. For board. Yeah, actually, I have put a scanner. Yeah. Oh, yeah, yeah. Your tongue. Yeah, yeah, yeah. Keep here. Become two. I don't give the
I can share.
pointer. Okay. Like it actually moves the slides. Changes.
उनका स्लाइड पर आपकी रखनी Oh, very bad. Very bad.
Give a signal of 3 minutes.
Okay.
So, welcome everybody for the final session of this workshop. It was very exciting for last 2 days, and in the morning we had a very interesting talk from three of the speakers. So the first speaker for today is in this session is Avinanda Chakraborty. She will be discussing about 2 nuclei and 1 galaxy, unveiling a closer dual AGN with HST and JWST.
Thank you, Sandeep, for my introduction. So I'm Avinanda. I'm a newly joined postdoc here. And thanks to the organizer, first of all, to giving me this opportunity to present here. So here I will work with Moushumi and Sudhanshu. And today the title of my talk is 2 nuclei, 1 galaxy, unveiling a closed dual AGN with HST and JWST. Okay, so today I'll talk about this particular dual AGN quasar. Why because so as we can see, this J07492255, this was an optically selected broad line quasar at a redshift of 2.17, which is a cosmic noon, so very high. So high redshift, large, it's a distant quasar. And there are very rare few number of quasars where we can actually resolve the host galaxy for the dual AGN or dual AGN candidates at this high redshift. So that's why this is a very interesting one, and that's why we have chosen this particular system for the work. So initially it was identified as a single quasar by SDSS, but later on it was flagged as a dual quasar candidate by the survey called VODCA. So I'll come to explain this, what this survey is in my later slide. So further, later on, by two instruments, high resolution instrument, one is HST and one is JWST. It was actually verified. So as the dual AGN quasar candidates, so HST snapshot program in these two filter imaging revealed that there are two cores with a separation of 0.46 arc second, that is 3.8 kiloparsec, so very close separation. And also in the left hand side, we can see this is an integrated flux map of joint H alpha and N2 from the JWST AF170 LP map, and this has also resolved it as two nuclei. So we can see there are 2 point sources at the center. And also from the JWST results, the quasar, it was found that the quasar, this quasar actually is 3 times brighter than this quasar. So these are the findings. Okay. So what is this method? I just spoke about. VODCA stands for Barstrometry for Off Nuclear Dual AGN. So which is basically it is a survey designed to identify for off nuclear or sub kiloparsec separated dual AGN, which has actually some of the quasars from some of the candidates later on actually confirmed using the high resolution instruments like HST and JWST. So what is this Bastrometry stands for? So this is a combination of variability and astrometry. And for those who are not familiar with the word astrometry, so astrometry is related to the position of the sources. So what is this method does? So for example, if we have two unresolved sources, so by unresolved, we mean if there are two sources, but still we cannot resolve that, we see them as a single point source. So what we are actually detecting is, as the position of the source is the flux weighted centroid. So if there are two sources, but we cannot resolve it, but still if there are two sources, so the flux will vary independently, maybe two or maybe just one of them will vary independently. So the centroid position will change with time. So these sources candidate for this method have been selected for this wide field survey, and they have been observed in time dependent shift, like in multiple epochs. So at different times, and those one who have shown a shift in the positions, though they were actually flagged as dual AGN candidates. And as I already mentioned, so later on, some of them actually have been verified by this high resolution imaging confirms as dual AGN, like instruments like HST and JWST. So whenever there is a dual AGN system or like candidates, so the main question arises is if it is a dual quasar or AGN system, or one of them is actually a lensed quasar. So one of the literature I have already worked on this, and they have analyzed so many things to get a confirmation about this, like if the system is a dual or it's actually one of them is a lensed galaxy. So this is one of their results, as I already showed. This is an integrated flux map from the JWST F170 LP. This is a near spec IFU data, And so they have found a very nice diffuse gas of H alpha and 2 central sources. And in the left hand side, they have also found, they have also checked for the aperture spectra. So in the central, so these are the spectra for the position enclosed by this aperture. So the central position, like the 2 sources and the center, shows very broad emission lines of H alpha and N2. And for these parts, shows narrow emission line of H alpha and N2. So basically, this is coming from the AGN and this is from the star formation. So actually from the galaxy. Okay, so they have done a lot of analysis, and some of their analysis actually support the lens theory, and some of them are actually supporting the dual theory. So I'll just briefly talk about of the analysis. So this is a combined spectra of both the quasars, both the actually dual AGN candidates, and okay, so there we can see that they have found it's just not only HST and JWST, they have also combined SDSS, Gemini also, and they have found that the quasar spectra, both components show very similar emission lines and spectral features. Also, they have found that they have similar black hole properties, comparable black hole mass and accretion rates. And also they have done the gas kinematics maps using a software called PyQSOFIT. And what they have found, so this is a radial velocity profile, and they have found there is actually looks like a rotating disk instead of a disturbed. So there's actually a very clear velocity gradient. One side is blue, one side is red, and this looks more like an undisturbed galaxy. And for merging system, we should expect some disruption, some disturbance, and also some tidal disturbance as like strong tidal disturbance, which is not showing here. So we can say these are the analysis which is supporting the lens theory. But there are some more also analysis which are supporting the dual AGN theory. So maybe the combined spectra look very similar, but when we are focusing on the JWST spectra, it's not exactly the same. So the continuum slope for both the quasar have different slope, particularly for this redward part of H alpha. This is maybe not very clear from the plots, but they have found that this red part shows a very different continuum slope. And also the narrow lines, the lines, emission lines shows different profiles. So one source shows very broad emission lines and other doesn't. It shows mostly the narrow emission line, and also the peaks of the emission lines for both the sources are a bit different. So that is actually supporting two systems. And so for all the lines, actually as I said, that the peak is there is a shift in the peaks. So overall, they have found a velocity offset of 200 km per second for all the emissions lines overall. And also, they have estimated the velocity from these emissions lines. So redshifts are also a bit different, but this is not all. So the spectral differences we can actually get if there are still lens, but the dust distribution is different around the different AGNs. So what they have checked for the H alpha by H beta emission line map, which tells actually the dust extinction of the system, and which is very consistent around the two AGNs. So basically, this is not explaining why there's a difference in the spectral properties. And also from the imaging, they have found that it looks more like two distinct AGNs in a different galaxies. Not like a lens system. And also there's a small detection of a tidal tail, which we see in the merging system. So these are the analysis which is supporting the dual system. So there are some supporting the lens, there are some supporting the dual. So there is no such confirmation from their analysis so far. So now there comes our work. So we have taken the archival HST images in two different bands and for our analysis, and we have decided, because they have already analyzed a lot about their AGN spectra and their gas kinematics, so we are not going to take their part because there's already a lot of observations. So we have decided to focus on the galaxies instead of the AGN two sources. So the two sources will take it, like we will not consider PSA, the central source, will focus on the galaxy. And if we can actually model it and can found any bulge inside it, so there will be a direct detection of galaxy mergers, because if two systems are merging, so there will be so many talks we have heard, and they have spoken about the bulges in the merging system. So if we can directly detect any merge, so we don't have to go look into this so many things that the other paper have already done. So it will be a straightforward checking. So for that, we have selected this HST images. Okay, so if we just focus on the central part, we can see that there are two sources for both the bands, and also there is some galaxy. We can see something like galaxy around it. So maybe the HST has detected the galaxy, so it's good for us. And also there is a PSF in the same image we have found for, like, it's there in the same image for both the bands. So PSF actually tells you how small a source can be detected by the HST. And we have found that the PSF size is very similar to the sizes of both the nucleus. It's a star map. Yeah, it's a stellar source. Okay. So we didn't just believe in our eyes that we got some host galaxy around the sources. So because galaxy detection is very important for us, because we are not focusing on the AGN, as I already stated. So what we did instead, so we have checked for the radial profile, and here we have taken the ratio of the with both the nuclei with the PSF in two different bands. And as I already stated, the PSF is a similar size with the AGN. So if there is no galaxy at all, there's no emission in the galaxy, so we should expect the ratio to be consistent with the with 1, because it's the same size, so same emission, so there will be nothing from the host galaxy. So for this 475 band, we can see the ratio is more or less consistent with 1. So we have very less hope, and that is also expected, because this is at redshift 2.17 is falling in the far UV part, and the far UV is coming from the broad line region from an AGN. So it should be AGN dominated. But the interesting part is for this filter. So here we can see the ratio is going very up. And it's also a bit expected, because this is actually falling at that redshift, falling in the near UV. Near UV comes from the star formation. So it's basically coming from the host galaxy. So it's great that we are actually getting, it's very hopeful that we are getting some emissions from the host galaxy. So we actually taken it forward, and we use the GalFit. So for GalFit, we actually, so it's basically the standard astronomical tool for extracting structural parameters for galaxy images to fitting analytic functions to their light profile. So basically we take the 2D image pixels, and it decides the best fit model for it using the minimum chi-square. So it actually can fit multiple components at the same time, like disk, bulge, and an AGN, to see how much light belongs to the each part. And also it takes accounts for the blurring of the system. So for the GalFit, actually for this image, we modeled with the GalFit, and this is the object, and we tried to model the two central source and the alongside the host galaxy. And this is the residual of our image, and we have found some pixels are brighter, and that can be, I mean, because GALFIT is basically for the structure parameters and structure models, and there can be some remnants which are not structured because it's a merging system at the end. So this is accepted. We have also found some parameters from here, and so we fitted the PSF to get the magnitude of the two sources, and also a Sarsic profile to fit the bulges around both the nucleus, and it's great that we could actually detect this is a bulge and this is a pseudo bulge around two sources, and their magnitude and their sizes. So it's great. But we also checked, so this is a surface brightness profile we checked, and so far we can see up to this, our model is fitting greatly, and this remnants maybe can come from the remnants on unstructured remnants, as I already said. So next we checked with this filter, but as I said, we do not have much hope from that, but we still checked. So this is our GALFIT, this is our image. We tried to fit the model, the two sources and the galaxy, and this is our remnant, as I said, unstructured. Here, unfortunately, we only detected the two sources, and they got their magnitude in this filter, and we couldn't see the bulges around each sources, but we could actually model, instead of that, model the disk, the common disk, and their magnitude and the size of it. Okay, so but it's not disheartening because in one of the filters we already detected the bulges. Okay, so the surface brightness profile is a bit like, I think there can be improvement. These are my preliminary results. So there is a scope of improvement for sure. So next, this is an ongoing work. We have taken the same JWST near spec image data that the Ishikawa has already used. So these are the two bands, two filters image we have taken. And as we can see, if we focus this part, so we can, in this filter, we can already see the host galaxy. So I'm really hopeful that maybe we can detect both the bulges and disk around both the sources. But unfortunately, it's a near spec IFU data, and GALFIT takes the imaging data, that is the photometric data. So we have to convert the near spec from the imaging. So for that, what we did is we collapsed the cube in the R band. So this is the like rest frame wavelength, and so because it's redshifted, so we have collapsed the image in this wavelength. And we have also subtracted the H alpha emission because H alpha is coming from the ionized gas, and we don't want that. We want the stellar structure that is that should come from the galaxy. So we just want the continuum. So what the next step is to convert that with the filter, because we need the synthetic photometry. But I'd like to draw your attention to this image, how beautifully the galaxy has been resolved. Like galaxy, we can see this in the R-band continuum image. So this is a very positive sign for us. So if we further continue with this, we may expect to detect both the bulges and the disk from this image. Okay, so from my very preliminary results, what I have found that we got the magnitude for both the sources in these two bands. In this band, we have found the bulges and got their magnitude and sizes. Here we got the common disk, but not the bulges, and its sizes as well. So most likely it's a dual AGN system. And what is left is, so now we have to do the GALFIT, and we are very hopeful to get the bulges and the disk from this R-band continuum image. And also we would like to repeat the gas kinematics for both the bands in JWST, and repeat the Ishikawa because we want to get the metallicity map. And that can also give us information about the galaxy merge, if it is a galaxy merger system or not. So, okay, so I'd like to conclude my talk. Thank you for listening, and I'm very open to any kind of question. I'm very happy to answer your questions. And this work I have done in 3 months. So it's all results are very preliminary. So I'm very open to any kind of feedback, suggestions on event collaborations. And I also work on star forming galaxy and its gas kinematics and radio loud AGN and its feedback. You can check here. And for any query or anything, you can reach out here. Thank you.
Thanks, everyone. We have time to kick one question.
I'm wondering, will you look at the color profiles?
Color profile, yeah, that is,
To
yeah, that is our actually plan, ma'am, because we have to, this is ongoing work, as I said. So yeah, that is actually a very good thing that can actually tell us a lot about it. So
because you have, what I noticed is that your UV profile of this thing actually increases as a function of radius. So
yes,
probably
yes,
the
yes,
staff mentioned either the dust is obscuring it or
yes, but the dust is not. That's what I'm saying, like, because the, I mean, the other paper, the,
stellar population gold in the center and
yeah, yeah, sure, ma'am. That's a very nice suggestion.
So okay, in the interest of time, we will move ahead, but I will encourage to discuss in lunch time. We can discuss. So let's, so next speaker is. Next and next speaker is Navya Saraswat. She will be discussing about entangling the stellar mass and environmental effects of AGN activity.
Yeah.
Signal for 3
So good afternoon, everyone. My name is Navya. And first of all, thank you to the organizers for such a nice workshop and for giving me this opportunity to present my work here. Today, I'll be talking about my master's thesis project, which was completed in TIFR Mumbai in the supervision of Professor Shadab Alam and Professor Shubhabrat Majumdar. This is not really related to galaxy mergers, but in this work, we tried to explore the AGN activity and environment connection. Understanding how galaxies evolve is one of the fundamental questions in cosmology. We know that most massive galaxies host a supermassive black hole at their center, which are observed as AGNs. And the growth of these objects can be tightly linked to galaxy evolution. But what exactly triggers AGN activity is still not fully understood. Some studies show that dense environments may trigger AGN activity through mergers, and some studies find no environmental dependence at all. So part of this discrepancy comes from selection biases and not isolating the stellar mass effects and the environmental dependencies. So in this work, we use a multi-wavelength catalog and a stellar mass complete sample to explore whether environment can independently trigger AGN activity and whether it can also affect the black hole accretion process itself. So to do this, we first construct a well-defined galaxy sample. So our pairing galaxy sample is drawn from the Galaxy and Mass Assembly Survey, which is a low redshift, highly complete spectroscopic survey covering 3 regions, G09, G12, and G15. For this analysis, we restrict our sample to the overlapping footprint of gamma G09, EFETS, DAISY Legacy, Galax, and we later also include DAISY DR1. And we also apply a redshift cut of 0.4. The figure on the right shows the spatial distribution of all these surveys used in our analysis. The X and Y axis are the right ascension and declination respectively. The table on the left shows, again, all the different surveys used in our analysis and what are the key tracers. For example, gamma G09 gives us the access to the photometric redshift, and DAISY Legacy survey provides us with the photometry. And similarly, Galax gives us the FUV and NUV information, which is useful for constraining stellar mass populations. EFETS is used, we use EFETS to later define our X-ray AGN sample, and we also include DAISY DR1 to access the black hole mass to later see the Eddington ratio distributions. So my first task was to cross match all these different catalogs that we used. So in our work, Gamma G09 was the central catalog. So what we did was to we iterated over every object in Gamma, and for the next respective catalog, we calculated the angular match distance using this formula, and we applied a tolerance of 0.001 radians. So this initial step, applying this initial step, we were ended with around 82,000 objects, which is our parent galaxy sample of Gamma G09. And the figure here shows the angular distance distributions of Gamma Ephets to the left and Gamma Daisy Legacy to the right. And you can see that for the Daisy Legacy histogram, there's another small peak here, which shows that the survey is relatively more deeper. And the vertical green and red lines show the galaxy size and cluster size respectively. Now the next task was to ensure that every object is matched to its correct counterpart in the other respective catalog. So to make sure that our sample was pure and complete, we divided the angular match distance that we calculated on the previous step with the X-ray uncertainty given in the EFITS catalog. Using this step, we got the angular distances in the units of sigma, and then we took a 5 sigma cutoff of these angular distances, and we were ended with around 4,892 objects, which we call as X-ray agents because they have a counterpart in the EFITS catalog. Now to get robust galaxy properties, we perform SED fitting using SIGAL. SIGAL is code investigating galaxy emission. It is an energy balance tool which balances energy between the absorbed UV optical light from the stellar emission and the emitted light in the W1 and W2 bands. And it uses a Bayesian framework to give us the best fit model. And it also includes a lot of different templates that we used. There were a lot of filters that were not already incorporated in SIGAL. So my first task was to incorporate the Galaxy FUV and UV filters. And then we, for the objects which didn't have an X-ray counterpart in EFETs, we mark them as X-ray non-detections, and we apply this upper limit of 1.5 times 10 raised to minus 6. These are the two representative SED figures. The only difference between these two is that in the right one, we have the right one is plotted for the object which does not have an X-ray detection. So the green triangle here shows the X-ray upper limit. The x-axis shows the observed wavelength, and the y-axis shows the flux density in millijansky. You can see that different colored components represent different emission from the galaxy. Like we have emission from stars, we have emission from dust and AGNs. So performing SED fitting using SIGAL gave us access to a lot of parameters for our galaxy objects. A few of them are plotted here. So these are histograms of stellar mass, star formation rates, and SED agent fraction for all galaxies from the Gamma G09 sample, and X-ray matched galaxies like the 4,000 objects that I previously talked about. I would like to mention the importance of incorporating Galaxy FUV and NUV filters here. This plot that you're seeing, initially we didn't include the Galaxy filters, and what we observed was as we went closer to the SED agent fraction 1, the number of X-ray matched objects were higher than the total galaxies. That means SIGAL was suggesting that the object was an AGN, but when we the survey was not suggesting so. So that's why we incorporated the Galaxy filters, and this helped us constrain the AGN population well. This figure here shows the stellar mass and redshift distribution of our 82,000 objects. And the red curve here shows the stellar mass completeness limit. How it was calculated was we looked at the stellar mass distribution in different tomographic bins, and usually stellar mass follows a salpeter-like function, but we looked at the turnover points and we fitted a 2D polynomial to it. So this is how this red curve was plotted, and we simply discard all the galaxies in this faint red shaded regions to ensure that our sample was stellar mass complete. So these are all the different AGN selections that we talk about in this work. We have X-ray agents that I've already talked about, which are all these objects that have a counterpart in IFET survey. Then we also include WISE agents, which are defined using the WISE color diagram. And we have broadline agents, which are defined using this criteria. Like we get access to the emission line information from DAISY DR1. And we have the classical BPT AGNs. So I'll show their distributions one by one. So the figure on the left shows the distribution of X-ray AGNs. The x-axis shows the observed X-ray flux in Earths per centimeter squared per second. And the vertical line here shows the IFET survey 90% completeness limit. And the right-hand side plot shows the WISE color diagram, and the polynomial here shows the Whitting et al. AGN region, which consists of our WISE AGNs, and the color bar here is the summed AGN luminosity. Similarly, this is the classical BPT diagram. These are all the demarcation lines, Kaufman and Cooley, and these are our BPT agents. And we've also plotted the Venn diagrams to show that there is a very little overlap between all these selections, to show that these all these species comes from very different populations. This is I would like to talk about this. So the way we formulate environmental parameters is to first we need to the goal is to calculate the tidal tensor field, and to do that we have to solve the Paulson equation in K space, which can be done using the fast Fourier transforms. And most of the surveys like SDSs, they are usually in the form of a light cone, and most of their volumes are empty. So the first step is to regularize the survey volume to ensure that most of the volume is not empty. So we regularize the survey volume, and then we calculate the local density field using Voronoi tessellation, and then the local density field is included here, and we get this Paulson equation, and from that we get the tidal tensor whose elements whose 9 components show the relative tidal field experienced by the objects. And we define these two environmental parameters here, which are the overdensity and tidal anisotropy. Overdensity is how much more dense or underdense the region is compared to the mean universe density. And tidal anisotropy is basically the relative force experienced by the two objects. So these are our two environmental parameters which we calculate from the gamma G0 survey. I'll quickly show our main results. So this is one of our key results. It shows AGN fraction as a function of the delta rank parameter that we introduced. Delta is the overdensity parameter. And we do this for 3 different AGN selections, the X-ray, WISE, and broadline. And we can see that in the case of X-ray AGNs, as we go from lower delta rank to higher delta rank, as in from low overdensity environment to high overdensity environment, there's an approximate 50% increase in the AGN activity. So this was really interesting, and this is not, so we do this for 2 different populations, star forming and quiescent galaxies, but this was not seen for other AGN selection methods, which shows that how the selection of AGN matters. And I'll quickly talk about this one more result. We also looked at the Eddington ratio distribution and Eddington diagrams of these objects for both higher overdensity and low overdensity environment. And we can see that both of these populations nearly occupy the same space. So we can, concluding this, we can say that environment does modulate AGN triggering, but it does not affect the black hole accretion process itself. So yeah, this was my work. Thank you.
That was a very interesting talk. No, thanks.
I know, very nice. But I have a question for your ACD modeling with cigar. So as per my knowledge, can you go back? Like, can you show? So as per my knowledge, the black curve actually is the total
Yeah.
flux.
Yeah.
And I don't understand why the stellar attenuation is higher than this total. It should be lower. I mean, can you explain like why it's so? Because if it is a superimposition of all the emissions, so it should go below, the black line should be above that.
Yeah, definitely. The thing is, this is not seen for all the objects. Like this is only seen for a few objects, and I agree. Like this was also confusing for me. Like for a few of the objects, the stellar emission is greater than the total fit model. So I'm not very sure. But yeah, this is something that we observed too.
Okay.
Yeah, I'm sorry, I don't know how to answer this question.
Okay.
But that U is stellar,
Unattenuated.
Unattenuated.
and attenuated is lying below. So, okay. Yeah. The yellow is lying below.
Okay, I see. Okay, so this is unattenuated. Okay.
Exactly.
Okay.
Any other question?
Also categorize the environments together, cluster environment. Yeah. Yeah. So, the value of tidal anisotropy is taken from the eigenvalues of tidal tensor, and these different eigenvalues correspond to different environments. For example, clusters, filaments, voids, and sheets. So these are the four environments, cosmic wave environments that we talk about. These depend on the eigenvalues of the tidal tensor.
So one quick question in the Eddington ratio. So you have a few candidates with the Eddington ratio greater than 1. So what are their, only one, I think.
Yeah.
So what is their environment typical, like it is very dense environment there?
Yeah, they lie in the high density region. There's only one.
Okay, so let's thanks again. The next speaker is Siddhant. We will be talking about gamma ray studies of galaxy merger, special association with Fermi-LAT sources and targeted searches for permanent merger systems.
Oh, sure. Okay. Slots. Yeah. Is it? Hi, I'm Siddhant, and we can skip this and go to lunch, or you can bear with me for next few minutes. Okay, so as Jaya and her group has already talked, that there are increasing evidence that galaxy mergers may power gamma ray emission. So here what we did is this work was basically motivated by their work, and we looked at spatial coincidences, and we also looked at some major mergers, and if we see any kind of gamma ray signatures coming from those. So yeah, this work was done with Shantanu at IIT Hyderabad. That data set and the pipeline. Now, the major thing is that it was 17 years of data. So you see a large astronomical data. The energy range was 1 to 300 GeV. The lower bound was because the point spread function is really bad at lower energy. So we avoided that data. And the upper bound was because the exposure area. So we did not wanted to include that. We looked at 10-degree box kind of a thing, basically. The others are basically your standard cuts and standard background models, all of which already Jay has talked about. She also talked about test statistics, so I don't have to repeat that. She had really made my work easier. But we know that anything greater than 9 or around 9 is a marginal evidence, and anything greater than 25 is a detection significance. We'll talk about SEDs later. This was from the Robert Song talk he gave, in which he showed using one Fermi-LAT data how much they had discovered in 1 year. This was just in 1 year. I just wanted to point it out. Okay. We started out from this data by Ackerman et al. 2018 paper. So this is their work, the thing they did where they trained the data, they validated, modeled it, Galaxy Zoo plus SDSS. They got a huge astronomical data set. So there are more than 3 lakh astronomical objects right there. What we did was, so we took this data and then we did a high confidence thing. So if there's a high chance of a 4-fold cross validation, that is a 95% or more chance that it's a galaxy merger. So then we put it in that. Then we cross matched it with SDSS and we took those where the R band magnitude flux is given. They basically gave us a 3,166 galaxy mergers, which are being shown here. So these are the galaxy mergers we basically looked at. Okay, and then what we did. Okay, so for this, we'll use the Poisson-based framework, so spatial matching criteria. For example, we did so there's a Fermi source right there, and then we plot a 4 sigma error ellipse around that, and we looked out for any kind of galaxy merger source nearby in that particular 4 sigma thing. And we also need to know that whatever we are seeing is not a chance coincidence. So we calculated an expected chance association where the formula given for mu, where A and B are semi-minor and semi-major axis, and we calculate the surface density of those mergers where the flux is greater than S. And then we calculated the probability of random coincidence, which was again given as following. We know that if P is small, then there's less chance of there's a low probability of random coincidence, and there's a reliable counterpart right there. This is basically based on Zhang et al. 2022 paper. The framework is based on that. What we found out was that there are 38 galaxy mergers, which were we found as a counterpart, the Fermi-LAT catalog. Out of those, 21 were there where the P value was less than 0.05. Now, out of those, 60% or around were blazars. So I don't think that interested much. But there were 5 of those, which accounts for 20 to 24%, which are unidentified sources. So they hint at a previously unrecognized population of gamma ray sources linked to galaxy mergers. Out of these, when we looked at the Simbat sources, we found that 2 of those have AGNs nearby. So we removed that also. Then we got 3 others where we did not see any kind of AGN, blazars, or anything. They could be plausible merger-driven gamma ray candidates. They are undetected in RAS and FIRST. We also calculated their flux ranges. We also did a control sample validation where we changed the RA index so that there's no chance coincidence. We found that it is not. We increased the threshold also. We found other blazars dominate. But the important thing was that we found 3 of those galaxy mergers, which I've shown here. So this is your 4 sigma error ellipse, right? And that is your Fermi source in blue and the merger right there. What you see is that the redshift is quite less. So they are at 0.06 and 0.08. And there are no AGNs nearby. There are no RAS or FIRST detections for there. So these could be the ones which are a counterpart to gamma ray sources. There was this other one also. Now, all 3 of them are coincident with normal galaxies at Z 0.07 to 0.09 with no multi-wavelength evidence for AGN contamination. And these are most compelling candidates for merger-driven gamma ray emission. Okay. Then what we did was we looked at 5 of those galaxy mergers, which contained your Taffy galaxies as well as NGC 3256, 660, and VV114. Again, the data set, I won't go into the description of it. You know it, a huge data set in 1 to 300 GeV ranges, standard bin likelihood, and calculating the spectral energy distribution plots, test statistics. The properties of those mergers are given here. So what is important was they were nearby, so there's high flux. There are large molecular gas reservoirs, and there are different merger stages. Okay. This table basically shows what we found. We found that for one of those NGC 3256, the evidence is almost 4 sigma, 3.9 sigma to be precise. These results also very well match with Ranjan Laha's work, Jaya's work. So yeah, the index we found was 2.05, which is basically in the hadronic regime, the pion decay one. It could point towards that. For other clusters, for other mergers, we did not find the test statistic to be that high. For NGC 660, it was there at 3 sigma evidence, but for others it was less. So we just calculated the upper limits. For NGC 3256, this is your spectral energy distribution plot, which shows that when we bend it into 5 different logarithmic bins, the first 4 bins basically shows the detection. And in each individual log bin, we see that there's a particular signal there as the test statistic value is greater than 9. But for only the last bin, we find the upper limit. The photon index again is 2.05, which is very consistent with the hadronic scenarios. We calculated the flux values. For 660, what we found out was that we only found out the upper limits, and those SED bins also just showed that all the test statistic values were less than 9. So there was no particular detection there. Okay. So for the first paper, what we did was we did a spatial coincidence between 3000 galaxy mergers with 4FGDL catalog using a Poisson-based elliptical association framework, found 21 secure associations. Out of that, 60% are your blazars, but some of them are not. We found 3 of them at which coincide with normal galaxies with no AGN signatures in SDSS, RAS, or FIRST, and these could be plausible merger-driven gamma ray candidates. The other way we did, we are one of the famous mergers. We looked at those and we tried to find out the gamma ray from that. From NGC 3256, you see a 3.5 sigma signal consistent with hadronic, the pion decay emission in a gas-rich starburst. No new point sources were found. So yeah, with that, I'd like to conclude. Thank you.
Thanks, Siddhant, for having me. So we have a couple of time for a couple of sessions. Right?
Yeah.
Make it control.
Oh, okay. Yeah, you're right. So it could be that because the normal galaxies, actually the counterparts which we found, which they are the normal galaxies. So there could be that normal galaxies could be the one. We did a control sample analysis where we changed the RAN deck, and then we looked at whether there's any chance coincidence, but we did not found any chance coincidence. But you are right about it that it's a very large elliptical error. So there could be an error that it is not exactly associated with a merger and it could be something else. So ideally, we could again do a control sample analysis with a larger sample of our normal galaxies mergers or just random RA decks and then see what happens. Oh, okay. So so most probably it could be hadronic, right? Because the index what we found was around 2.05 or something like that, right? So that basically tells us that pion decay could be the reason, but we can't be sure without having more study on it.
So I wanted to ask, these are mergers.
Yeah.
There's star formation as well as AGN activity. So where is the gamma coming from, star formation or from the AGN?
Oh, okay, so we did not found any AGN counterpart. So I think it's most probably from the star forming reasons, and because we looked at AGNs, in a few of those we did not found any AGNs nearby. So could possibly be because of star formation. Yeah.
3256 has AGN?
Yeah. Actually, this one has the 3256. Yeah, the 32561. This one basically has a AGN nearby. So this one could be basically because of the AGN actually, the 3.5 sigma signal. Yeah. Yes.
Okay, so with this, we thank all the speaker of the session. This is the end of the workshop, and I will like to invite Siddhant for giving summary and the thanksgiving to all the hardworking organization.
So, well, it's very difficult to provide the meeting summary because there were the talks from various topics. So I will go ahead and I will thank all the participants. I will thank all the speakers who has given the excellent talks, excellent presentations. And I hope you had a very good discussions, and it would be good if some collaborations can be come out from this workshop meeting. So thanks, my thanks to all the speakers and presenters, including the poster presenters as well. Now, obviously, it's time to thank all our organizers. So we have an excellent set of people who has done a very hard work to organize this people. So our local organizing committee led by Chandan, Terry, I would like to ask so, they are running around and making sure that everything is running smoothly. Also, we should thank Vikrant. He is helping us. And of course, the Yogesh, yes, he's not here, but he helped us a lot immensely in the first day when we were in the Survey of India building. I would also like to thank our canteen staff, our housekeeping staff, and staff at Bhaskara, who helped us to manage this meeting. And of course, I would like to thank our director, Annapurni, as well, who has provided a lot of strategic and at last, Moshmi, because all this is possible because of the grant. So thanks, Moshmi. And I think, yeah, that's all. We have a very, I guess, fruitful meeting, and maybe if we have more grants in the future, you can organize more such meetings. Yeah, thank you, everyone.
So lunch is there.
Yeah, lunch is there, so we can go for the lunch.
Yeah.
Just